Welcome back, everybody. Today we're going to talk about what makes a relation into a function. Again, a function is a subset of the relations, meaning all functions are relations, not necessarily all relations are functions. Very often we use an arrow diagram to represent our domain and range. And here I'll put a couple of domain points. And then we draw basically arrows, right? Here's the rule. From each one. All right, so this would be a pictorial representation of a function. If I were to write this out in words, I would say a function is from a function from x to y. Say it better. Or domain to range is a relation that associates each element of x to exactly one element in y. All right. So let's take a look at a quick example to really put this into a context. All right, so here we go. All right, my example, my rule is going to be y equals 2x plus 3. And the question is it a function? All right, so x, well, I'm going to make a table of values. Plug in 0, I get 3. I plug in 1, I get 5. I plug in 2, I get 7. And it looks to me like no matter what value I plug in, I'm going to get a different value for y. So 0 can only go to one value, 1 can only go to one value in y, and so on and so forth. Therefore, you can say that yes, this is a function. All right, let's take a look at another one. Let's take a look at something that's not linear. Y equals x squared. Why don't you take a moment, do a table of values, and think about whether this is or is not a function. All right, so let's make that a quick table of values. Again, your table and my table don't have to be the same. We just need to come to a similar conclusion. So I'm going to plug in -2, I get 4. I plug in 0, I get 0. I plug in 2, and I get 4. All right, so how does example 1 differ from example 2? Well, very clearly, right here, I plug in 2 different values for x, and I get the same value for y. The question is this a function? Let's go back to our definition for just a second. A function associates each element in x to one element in y. So I have the element -2 associates with 4, right? Does -2 associate with any other element in y? The answer is no. It only associates with 4. That's okay that +2 associates with 4 because +2 doesn't associate with any other element in y except for 4. So the conclusion is that yes, this is a function. All right, let's try, I'm going to just tweak the last example just a little bit and say x equals y squared. And let's try that table of values one more time. All right, so if I plug in -2 for y, what do I get? I get 4 for x. If I plug in 2 for y, I get 4 for x. So 4 associates with two different elements in y. 4 associates with -2, and 4 associates with +2. In this case, this is not a function. Because it doesn't fulfill that definition. All right, well, once we know we have a function, there is something called domain and range. Now, domain is primarily what I'm going to focus on, but range is probably something that you've done before, so you will be expected to be able to do it, all right? But let's focus on domain, all right? The domain, all right, is what x is allowed to be. Not a very mathematical definition, but, you know, it's true. So I kind of have a rule for domains, right? I say all domains start with all real numbers. And there are only there's two reasons you would restrict the domain. All right, the first reason is the value of x will result in a 0 in the denominator all right, and the second reason would be that the value of x would result in a negative under a radical symbol, under square root. Under the square root sign. I'm going to try two examples and we'll see how we do. All right, so here's the first example. I'm going to give a function. And I'm going to say the question is find the domain. Very straightforward question. However, if you can't find the domain, you really can't do anything else with it. So any domain is going to start with all real numbers. But what do we have here? We have a denominator. And what are we not allowed to have? A value of x that will result in a 0 in our denominator. So the question is, what value will result in a 0? And we can eliminate that value or values. So if I say 1 minus x squared equals 0, and I solve this equation, I'll know what values I can't put into my domain. All right, so I'm going to add x squared to both sides. And I get plus or minus 1, which means basically that when I write my final answer, and in this case, interval notation is indeed warranted. All right. So negative infinity up to -1, and I'm going to put a parenthesis because I can't include -1. in union with negative 1 to 1, another parenthesis because I can't include 1, 1 to infinity. And remember, infinity gets parentheses on either side. All right. So, the next example I'm going to take a look at is one with a square root. So I have f of x equals 1 over the square root of x minus 1. So now I have two things that I really need to take a look out for. I need any value of x that will make the denominator equal 0 has got to be gone. All right? So x equals 1, right, is not in the, I'm going to call that domain. In a lot of cases, it's going to be a lot easier to figure out what numbers are not in the domain and then give your final answer of, here's all the other numbers. Now, the other thing we need to do is we need to figure out what values of x will make the result a negative number under that square root, and we got to eliminate those. So anytime x minus 1, right, is less than 0, right, those are going to be bad numbers, right? So what we can do is we can say x minus 1 has to be greater than 0, and these numbers are good, right? All right, so x has got to be greater than 1. If x is greater than 1, right, that would result in a positive number under the radical symbol and not give a result under 0, right, of 0. So how are we going to write our final answer? We write our final answer by saying 1 to infinity. Why can't we give any numbers that are less than 1? Right? If I plug in a half or I plug in negative 2, right? Those will all give negative numbers under that radical symbol. All right. I took it for granted that we were calling these functions, but there is a way to figure out if you have a function or not based on being given a graph. And that's called the vertical line test. And what the vertical line test says is that if you can pass a vertical line through your function and it hits in only one point, then it is a function. All right, so I'm going to make a graph. All right, and I'm just going to make one for example purposes to kind of show you what I mean. I'll take my ruler, connect the dots, and then we will talk about the vertical line test. All right. There's my function, right? And it goes on forever both ways. And what the vertical line test says is that if I have a vertical line and I pass it through my function, it should hit the function in only one point, no matter where the vertical line is. So I'm going to change colors just so we can differentiate. So I just passed a vertical line through my function. It hit only one point. Let me try a different spot. Yep, did it again, only hitting 1 point. Try again. Yep, in 1 point. Therefore, I can conclude that yes, this is a function. All right. Let's give another example. All right, and hang on. X equals y squared. Now that graph, we already said, kind of looks like this. All right, so now let's take our ruler. Did I pass my vertical line through my function and I hit it in more than one point? If I can do that even once, no, it's not a function. So right here, I could say that this is not a function based on the vertical line test. All right, so one of the last things I want to do is just a little bit of function arithmetic. This is probably things that you've seen before. So I'm going to start with the example and just kind of work my way through it a little bit. So example, all right, consider the function. X over x plus 1. All right, question A says, is the point (1, 1/2) on the graph of f? Basically what it's saying is 1, -1 part of that function? So the strategy here is this. I'm going to take 1 and 1/2, substitute them in for x and y, or x and f of x. If it turns out to be a true statement, then 1, 1/2 is indeed a part of that function. So I can start by changing, I'm going to change color just so we can differentiate f of x to y. We all agree that f of x changes to y. And now I'm going to substitute in 1, 1/2, all right? So I have 1/2 equals 1 over 1 plus 1. And I can see very clearly that that makes a true statement. So yes, the answer to A is yes, it is on the graph. All right, so question B says, if x is 2, what is f of x? I'm going to rewrite my function so I don't have to keep scrolling up and down. Basically, what I really need to do is just replace, anytime I see an x, just replace it with a 2. So I have 2 over 2 plus 1. And my answer is 2/3. All right, so the last one, so part C says, if f of x equals 2, find x. So if my function looks like this, basically what I need to do is I need to take 2 and take f of x and replace it with 2. So 2 equals x over x plus 1. Then I'm going to multiply both sides times x plus 1, and I get 2 times x plus 1 equals x. Then I can distribute, and I get 2x plus 2 equals x. And now I can subtract 2x from both sides. And I get 2 equals -x, or x equals -2. Hence, I have answered the question. The last thing we're going to do is talk about some applications. Now, when you're talking about functions, all right, there's a wide variety of applications. And the context of the problem can be a variety of different things. If you're looking to do every context in class, there's just not enough time for that. So what you need to do is look for the different concepts that the problems are doing and not get caught up in the context. All right, let's try this one as an example. Metro Entertainment Group spent $100,000 on the production cost for its off-Broadway play, Bride and Prejudice. Once the play runs, each performance costs $1,000 and brings in $2,400. A, find a cost function. B, find a revenue function. And then C, find out how many shows are needed to break even. All right. So for my cost function, I'm going to use certain things. I'm going to use this $100,000. And I'm going to use that 1,000 because those are the things that go into the cost. All right, so $1,000 per show, and I'm going to call each show X, plus $100,000 to make the shows to begin with. There's my cost function. My revenue function is how much money the play brings in. And what do we see from is that we bring in, I'll use green for money, we bring in $2,400 per performance, which means that I could say it's 2,400x. Now C wants to know how many shows are needed to break even. So the question is, when does, that's terrible writing, I'll make that better. When does the cost equal the revenue? When do they balance out? So if I put 1,000x plus 100,000 equals 2,400x, we can work this down. I can subtract 1,000x. So I have 1,400x equals 100,000, right? And I can quickly divide by 100. I have 14x equals 1,000. So now I'm going to divide by 14. And I wind up getting x equaling 71.43 shows. You're always welcome to check my math. I always want you guys to keep me honest. However, we can't have 0.43 of a show. If you're coming in and I only give you 0.43 of my show, you're going to want your money back. Hence, I will not break even. So what do we need to do? We need to take that and make it 72 shows to break even. 71 shows is not enough. 72.43 shows is a cruel joke on that last audience that gets less than half a show. So we have to do 72. And 72 will yield a little profit, but it is the minimum amount you can do to break even. All right, guys, I want to thank you guys for listening. There's much more practice that needs to happen, but at least you guys got a good start, and I'll see you all next time. Thank you, and I look forward to seeing you soon.